The universe is filled with bright objects. One can see thousands of stars with the unaided eye on a clear night. It took perhaps 100 million years after the Big Bang for the first stars to form, and nearly a billion years for galaxies to proliferate throughout the universe. Welcome back to my channel. The first stars in the universe. The formation of the first stars was an epochal event that fundamentally altered the universe's subsequent evolution, as suggested by the novel models. These stars modified the cosmos dynamics by heating and ionizing the encircling gases. Early stars produced and dispersed the first heavy elements, paving the way for the eventual formation of solar systems similar to ours. And the collapse of some of the first stars may have fostered the growth of supermassive black holes that formed at the center of galaxies and evolved into the dazzling power sources of quasars. Briefly, the earliest stars enabled the formation of the universe we observe today, including galaxies, quasars, planets, and humans. Lack of direct observations hinders the investigation of the early universe. The oldest galaxies and quasars observed to date back approximately a billion years after the Big Bang, presuming the universe is between 12 and 14 billion years old. A billion years after the Big Bang, some luminous galaxies and quasars had already appeared, indicating that the first stars must have formed earlier. The background radiation reveals evidence of small-scale density fluctuations in the primordial soup, despite the fact that the early universe was remarkably uniform. According to cosmological models, these clusters would progressively transform into gravitationally bound structures. The denser regions would create a network of filaments, and the first star-forming systems, the so-called small protogalaxies, would coalesce at the network's nodes. The protogalaxies would then merge to create galaxies, and the galaxies would assemble into galaxy clusters. Even though galaxy formation is largely complete, galaxies are still assembling into clusters, which in turn are aggregating into an immense filamentary network that spans the universe. According to cosmological models, the first small star-forming systems should have emerged between 100 and 250 million years after the Big Bang. These protogalaxies would have been 100,000 to 1 million times more massive than the Sun and approximately 30 to 100 light-years in diameter. These characteristics are comparable to those of the molecular gas clouds in which stars are currently forming in the Milky Way, but the first protogalaxies would have possessed fundamentally distinct characteristics. For starters, they would have been composed primarily of dark matter, the hypothetical fundamental particles that make up approximately 90% of the mass of the universe. In protogalaxies, however, conventional matter would have coexisted with dark matter. The second significant distinction is that protogalaxies would have contained only trace quantities of elements other than hydrogen and helium. The Big Bang produced hydrogen and helium, but the majority of heavier elements are only produced by thermonuclear fusion reactions in stars, so they would not have existed before the formation of the first stars. The juvenile metal-rich stars in the Milky Way are referred to as population 1 stars, while the old metal-poor stars are referred to as population 2 stars. Consistent with this terminology, the stars with no metals whatsoever, the very first generation, are sometimes referred to as population 3 stars. In the absence of metals, the physics of the first star-forming systems would have been considerably simpler than that of modern molecular gas clouds. In addition, cosmological models can, in principle, provide a comprehensive description of the initial conditions that preceded the formation of the first generation of stars. In contrast, stars formed from molecular gas clouds are born in environments that have been altered by previous star formation. Therefore, it may be simpler for scientists to model the formation of the first stars than the formation of stars today. In any case, the problem lends itself well to theoretical investigation, and a number of research groups have utilized computer simulations to depict the formation of the first stars. Simulations indicate that primordial gas clouds would form at the vertices of a small-scale filamentary network and then contract due to gravity. The gas would be heated to temperatures above 1000 kelvins due to compression. In the dense hot gas, some hydrogen atoms would combine to form trace quantities of molecular hydrogen. After colliding with hydrogen atoms, the hydrogen molecules would begin to cool the densest portions of the gas by emitting infrared radiation. The temperature in the densest regions would decline to between 200 and 300 kelvins, lowering the gas pressure and allowing these regions to contract into gravitationally bound clumps. This cooling is essential for the separation of the conventional matter and dark matter in the primordial system. Hydrogen that has cooled forms a flattened, rotating configuration that is clumpy, filamentous, and potentially disc-shaped. Dark matter particles would not emanate radiation or lose energy, so they would remain dispersed throughout the primordial cloud. The star-forming system would resemble a miniature galaxy, complete with a disk of normal matter and a halo of dark matter. Within the disk, the densest clusters of gas would continue to contract until some of them underwent a runaway collapse and became stars. The first star-forming clusters were significantly hotter than the molecular gas clouds where the majority of stars are presently formed. Dust particles and molecules containing heavy elements significantly reduce cloud temperatures to approximately 10 kelvins. This mass is proportional to the square of the gas temperature, and inversely proportional to the square root of the gas pressure. The pressures of the first star-forming systems would have been comparable to those of present-day molecular clouds. Due to the fact that the temperatures of the first disintegrating gas clusters were nearly 30 times higher than those of molecular clouds, their mass would have been nearly 1,000 times greater. If we scale up by nearly a factor of 1,000, we can estimate that the masses of the first star-forming clusters were between 500 and 1,000 solar masses. In accordance with this prediction, all of the aforementioned computer simulations demonstrated the formation of clusters with masses of at least several hundred solar masses. The calculations indicate that the predicted masses of the first star-forming clumps are not overly sensitive to the presumed cosmological conditions, such as the precise nature of the initial density fluctuations. One reason is that molecular hydrogen cannot cool the gas below 200 kelvins, making this the minimum temperature for the first clusters of star formation. A second reason is that the cooling from molecular hydrogen becomes ineffective at higher densities when aggregates begin to collapse. At these densities, hydrogen molecules collide with other atoms before they can emit an infrared photon. This raises the gas temperature and delays the contraction until the clumps have amassed a few hundred solar masses. What happened to the initial clusters that collapsed? Did they form stars with masses comparable to their own, or did they fragment into numerous smaller pieces and form numerous smaller stars? The research teams have advanced their calculations to the point where the clumps are well on their way to becoming stars, and none of the simulations have revealed any tendency for the clumps to fragment. Observations and simulations indicate that the fragmentation of star-forming clusters is typically limited to the formation of binary systems. Fragmentation seems even less likely to occur in primordial clusters, as the inefficiency of molecular hydrogen cooling would maintain the mass at a high level. Simulations have not yet conclusively determined the ultimate outcome of collapse, and the formation of binary systems cannot be ruled out. How did these initial stars influence the remainder of the universe? Importantly, the surface temperatures of metal-free stars are higher than those of stars with compositions similar to the Sun. Without metals, the production of nuclear energy at a star's core is less efficient, and the star would need to be heated and denser to produce enough energy to counteract gravity. Theoretical models of such stars with masses between 100 and 1,000 solar masses were developed by scientists. The models revealed that the surface temperatures of stars were approximately 100,000 kelvins, which is approximately 17 times higher than the surface temperature of the Sun. Therefore, the first starlight in the universe would have consisted primarily of ultraviolet radiation from extremely hot stars, and it would have immediately begun to heat and ionize the neutral hydrogen and helium atmosphere surrounding these stars after their formation. This event is known as the cosmic renaissance. Although astronomers are unable to estimate how much of the universe's gas condensed into the first stars, a fraction as small as 1 part in 100,000 may have been sufficient for these stars to ionize the majority of the remaining gas. Once the first stars began to shine, expanding bubbles of ionized plasma would have formed around them. Over hundreds of millions of years, as more and more stars formed, the pockets of ionized gas would have merged, and the intergalactic gas would have become completely ionized. Recently, researchers from the California Institute of Technology and the Sloan Digital Sky Survey discovered evidence of the final phases of this ionization process. In the spectra of quasars dating back roughly 900 million years after the Big Bang, the researchers observed a strong absorption of ultraviolet radiation. The results indicate that at that time, the final regions of neutral hydrogen gas were being ionized. Helium requires more energy to ionize than hydrogen, but if the initial stars were as massive as predicted, they would have simultaneously ionized helium. Alternatively, if the first stars were not quite so enormous, the helium must have been ionized by sources such as quasars emitting energetic radiation. Future observations of distant objects could help determine when helium became ionized in the universe. If the first stars were indeed extremely massive, they would have lived for only a few millions of years. At the conclusion of their lives, certain stars would have exploded as supernovae, expelling the metals they produced through fusion reactions. It is predicted that stars with masses between 100 and 250 times that of the Sun will explode violently, and it is likely that some of the first stars had masses in this range. Due to the fact that metals are much more effective than hydrogen at cooling star-forming clouds, and allowing them to collapse into stars, the production and dispersion of even a small quantity could have had a significant impact on star formation. When the abundance of metals in star-forming clouds exceeds 1,000th the abundance of metals in the Sun, the metals swiftly cool the gas to the temperature of cosmic background radiation. As the universe expands, this temperature decreasing from 19 kelvins a billion years after the Big Bang to 2.7 kelvins today. This efficient cooling permits the formation of stars with reduced masses and may also significantly increase the overall birth rate of stars. In fact, the rate of star formation may not have accelerated until after the first metals were produced. In this instance, second-generation stars may have been primarily responsible for illuminating the universe and sparking the cosmic renaissance. At the beginning of this active period of star formation, the cosmic background temperature would have been higher, at about 10 kelvins, than the present-day temperature of molecular clouds. Prior to this temperature decrease, which occurred approximately 2 billion years after the Big Bang, the process of star formation may have still favored massive stars. As a result, it is possible that a significant number of these stars formed during the early stages of galaxy formation, when successive protogalaxies merged. When two galaxies collide and cause a starburst, an abrupt increase in the rate of star formation, an analogous phenomenon may occur in the modern universe. Presently, such occurrences are relatively uncommon, but evidence implies they may generate a substantial number of massive stars. This hypothesis regarding the formation of the first stars may help to explain some perplexing features of the current universe. Galaxies contain fewer metal-poor stars than would be anticipated if metals were produced at a rate proportional to the rate of star formation. This discrepancy could be resolved if early star formation had produced relatively more massive stars. Upon their demise, these stars would have dispersed significant quantities of metals, which would have been incorporated into the majority of the low-mass stars that we observe today. The large abundance of metals in the hot, X-ray emitting intergalactic gas in clusters of galaxies is another puzzling feature. This observation is most readily explained if there was an early period of rapid formation of massive stars, and a correspondingly high rate of supernovae that chemically enriched intergalactic gas. The case for a high supernova rate in the early universe is also consistent with recent evidence indicating that the majority of ordinary matter and metals lie in the intergalactic medium rather than in galaxies. Galaxy formation must have been a spectacular event, involving intense spurts of massive star formation and barrages of supernovae that expelled most of the gas and metals from the galaxies, in order to produce such a distribution of matter. Stars with masses greater than 250 times that of the Sun do not explode at the conclusion of their lives. Instead, they collapse into black holes of comparable mass. Several of the aforementioned computer simulations predict that some of the first stars would have had masses of this magnitude. Due to the fact that the first stars formed in the most dense regions of the universe, any black holes that resulted from their collapse would have been absorbed through successive mergers, into systems of increasing magnitude. It is possible that some of these black holes became concentrated in the inner regions of large galaxies, and fostered the growth of the supermassive black holes found in galactic nuclei, which are millions of times more massive than the Sun. In addition, astronomers believe that the source of energy for quasars is the plasma that spirals into the black holes at the centers of large galaxies. If smaller black holes had formed in the centers of some of the earliest protogalaxies, the accretion of matter into the holes could have produced mini quasars. Due to the fact that these objects may have appeared shortly after the first stars, they may have provided an additional source of light and ionizing radiation in the distant past. With the formation of the first stars and protogalaxies, cosmic evolution began. Numerous pieces of evidence indicate that the period of most intense star formation, galaxy formation, and quasar activity occurred a few billion years after the Big Bang, and that all of these phenomena have continued at progressively slower rates as the universe has matured. As clusters of galaxies assemble, the majority of cosmic structure formation has migrated to larger scales. Clouds of gas drifting through the early universe have provided astronomers with a glimpse of the remnants of the first ever born stars. Not the stars themselves, they are long gone, having burned hot and rapid before exploding in a supernova that our instruments are unable to detect. However, the debris left behind by these eruptions reveals the products of the nuclear fusion that occurred in their cores. First ever identification of chemical traces of the detonation of the first stars in extremely distant gas clouds. According to the currently accepted cosmology, there was a time in the history of the universe when everything was bleak. Before 13.8 billion years ago, when the universe was much smaller, it was filled with a hot, murky atmosphere of ionized gas that prevented light from traveling throughout the universe. Any photons would have dispersed from unbound electrons. Protons and electrons recombined into neutral helium and hydrogen, once the universe had adequately cooled down. After the birth of the first stars and galaxies, when their ultraviolet radiation re-ionized the neutral hydrogen, the entire electromagnetic spectrum became accessible to light. We believe the first stars appeared between 13.7 and 13.4 billion years ago, but we have never seen one. They are known as population 3 stars, and they were likely vastly different from the stars we see today. They could have been massive, in which case they would have burned out rapidly, culminating in supernova explosions that ejected their contents into space, to be absorbed by the subsequent generation of stars. However, heavy element production requires stars. Population 3 stars were composed primarily of hydrogen and helium because these elements were the only ones present in the universe at the time of their birth, with trace amounts of lithium, the third lightest element. However, the nuclear factories in their cores fused the atoms of these elements to produce heavier ones, such as carbon, oxygen, and magnesium, which were then dispersed throughout space when the star erupted. That does not imply there are no traces of them left. By detecting the chemical elements they released into their surroundings, after their demise, primitive stars can be studied indirectly. The scientists used the X-Shooter instrument on the Very Large Telescope of the European Southern Observatory to analyze the light of extremely luminous, distant galaxies known as quasars. As this light travels through space, it sometimes passes through material clouds. As wavelengths are absorbed and re-emitted by cloud particles, this can alter the light slightly, making some portions of the spectrum brighter or dimmer. Scientists can examine these signatures in a spectrum in detail and correlate them to particular elements. The researchers collected observations of 54 such clouds of material, and searched for remnants of the elements that are likely to be dispersed through space by population 3 stars, along with a small amount of heavier elements such as iron. They discovered the signature they were searching for in 3 clouds, dating to roughly the first 1 to 2 billion years after the Big Bang. Carbon and oxygen were abundant in these 3 clouds, and their magnesium to iron and silicon to iron ratios were in excellent agreement with those of ancient, nearby stars with low heavy element content. In the coming years, scientists hope to learn more about the story's earliest phases, when structures began to form on the smallest scales. Due to the likelihood that the first stars were extremely massive and bright, instruments like the Next Generation Space Telescope, the intended successor to the Hubble Space Telescope, could potentially detect some of these ancient bodies. Thank you for watching.